We've all seen the shocking news reports: a building, sometimes decades old, sometimes still under construction, suddenly gives way and collapses into a pile of rubble. It's a terrifying thought, but these tragedies are almost never truly sudden or unexpected. In the world of structural engineering, a collapse is almost always the final result of a chain of failures, a sequence of overlooked warnings, calculated risks, and violated principles. So, what actually causes a sound, solid structure to fail? The answer is rarely a single thing. It's typically a cascade of events, where one weakness exposes another, until the entire load path is severed. In this video, we're moving beyond the headlines to perform a forensic engineering analysis. We'll break down the 5 most common categories of building collapse, explaining the structural mechanics behind each one, from foundation failures to progressive collapse. By understanding these failure modes, we can build a world that is inherently safer and more resilient. Let's start with what is arguably the most critical phase: design and conceptual flaws. Before a single shovel hits the dirt, a building's fate is largely sealed on the drafting table. A fundamental design error creates a built-in weakness that may lie dormant for years until the right trigger appears. This can include incorrect load calculations, where the engineer underestimates the actual dead and live loads the structure will bear. A classic example is the infamous Hyatt Regency walkway collapse in Kansas City, where a last-minute design change to a connection detail doubled the load on a single support rod, leading to a catastrophic failure under the weight of partygoers. Another critical design flaw is the creation of a soft story. This is when one floor, typically the ground floor with large open spaces for parking or retail, is significantly less stiff than the floors above. During an earthquake or under extreme lateral load, this weak story acts as a hinge, buckling and causing the upper floors to pancake down. This was a major factor in the collapse of many buildings during the 1995 Kobe earthquake. A pro tip for architects and engineers is to rigorously model load paths and never make assumptions about connections. Every single load must have a clear, continuous, and adequately designed path to the ground. Even with a perfect design, a building can be doomed by construction and material failures. This is where the theoretical design meets the messy reality of the site. Common failures include substituting specified materials without engineering approval, such as using a lower grade of rebar or concrete with a higher water-cement ratio that drastically reduces its strength. Poor workmanship is another massive factor, like improperly splicing rebar, underfilling concrete in formwork, creating honeycombing, or incorrectly torquing high-strength bolts in a steel frame. Perhaps the most dangerous practice is the unauthorized removal of structural elements during renovation, such as cutting a load-bearing wall or column to create an open floor plan without installing a proper transfer beam. A common and catastrophic on-site mistake is stripping formwork from a concrete element too early, before it has gained sufficient strength to support its own weight and the construction loads above it. This lack of quality control during the construction phase can introduce fatal weaknesses that the original design never accounted for. The third major category is foundation failure. The entire building, no matter how well designed and constructed, rests on this base. If the foundation fails, everything above it is compromised. This can happen due to a variety of geotechnical issues. Differential settlement occurs when parts of the building sink more than others, often due to unstable or varying soil conditions that weren't properly identified in the geotechnical investigation. This twisting of the foundation can shear columns and rupture load-bearing walls. Landslides or soil liquefaction during an earthquake can completely remove support from under a foundation. A pro tip from geotechnical engineers is that water is often the trigger. A change in the water table, poor site drainage, or a burst pipe can erode supporting soil or dramatically increase the load on retaining walls, leading to a catastrophic foundation shift. Perhaps the most dramatic and insidious type of failure is progressive collapse. This is when a local failure, like the loss of a single structural column, propagates through the building, causing an entire section or even the whole structure to collapse. Think of it like pulling a single card from a house of cards. The classic example is the Ronan Point collapse in London in 1968, where a minor gas explosion blew out a single load-bearing wall in a precast concrete panel building, leading to the progressive collapse of an entire corner of the high-rise. Modern building codes, especially after 9/11s, now include requirements for disproportionate collapse prevention. This means designing structures with redundancy, so if one member fails, alternative load paths exist to bridge the gap and prevent the failure from spreading. This is achieved through strong, continuous ties throughout the structure and the design of key elements to resist specific threats. Finally, we have external causes and overload. This includes the forces of nature that may exceed the building's design capacity, such as a massive earthquake, a hurricane with winds stronger than code requirements, or unprecedented flooding. However, it also includes human-made overloads. A tragic example is the collapse of a library floor at a university, where the sheer weight of students and books during an exam period exceeded the design live load. Another factor is a lack of maintenance, where decades of water ingress corrode steel supports or rot wooden beams, slowly reducing their capacity until they can no longer carry the load. To summarize the key takeaways: 1. Collapses are rarely from a single cause but a chain of failures in design, construction, and maintenance. 2. Design flaws like soft stories and connection errors create inherent weaknesses. 3. Poor construction practices and material substitutions can fatally compromise a sound design. 4. Foundation instability is a critical failure point. And 5. Progressive collapse can turn a local incident into a total catastrophe, which is why structural redundancy is so vital. Now I want to hear from you. In the comments below, which of these failure modes do you find most critical to guard against in your work? Is it ensuring design redundancy, enforcing strict quality control on site, or conducting thorough geotechnical investigations? Your perspective is crucial. If this forensic look at building collapses has been valuable, please give this video a like and subscribe.